I would like to thank organizers for inviting me here. Just before starting, I want to make a little remark about organizers, because after 2 attempts which failed, now we have a 3rd attempt finally. But it seems that during these 2 attempts, the organizers became either too pessimistic or too optimistic. Because in the title, if you read it carefully, it is claimed that we are going to celebrate 102 factorial of that, which either they lost the hope to make, and they shifted it to this year, or maybe they're too optimistic and they think that even in this year, Ising model we will celebrate it. Okay, so I'll be talking about 2-dimensional Ising model with disorder, with quenched disorder, and in particular critical properties, but I prefer to start from, not from the very beginning, but just a long preface. First pure Ising model, then what we did with my brother Volodya 40 years ago about the critical behavioral specific heat, and finally something more recent about non-self-averaging in the critical point. But the starting point is this fermion representation. So if you if you concentrate only on the critical properties, then in principle you have to start from the lattice formulation, and then through painful procedure you come eventually to a continuum limit. And if you do it in terms, if you start in terms of Grassmann variables, which are 4 component, in a continuum limit near the critical point, you find that the system is effectively, the singular part of thermodynamics is effectively described by 2 component Grassmann Majorana fermions. So the starting point for today, that was made, I think, I was not born by that time, so it's a very long time ago, but still. So it's described in terms of 2-dimensional Hamiltonian like this, 2 psi like this, and psi is the 2-component Majorana field, and Majorana means that it's real real Grassmann variable, so that here when we write this, it doesn't mean that it's a complex conjugate. Just by definition, it's a sigma 3 psi, and this is a Pauli matrix, and this means sigma 1 d over dx plus sigma 2 d over dy Pauli matrices. Then formalism of this representation tells that these objects are anti-commuting alpha psi beta x prime is equal to minus beta x prime alpha x, and on top of that one have to introduce by definition the integration rules. When I want to use this to compute the partition function and the free energy, you need to know what does it mean this. So rule, by definition, this is 0. By definition, dx psi alpha x is equal to psi alpha x dx minus, here the anti-commuting, pardon, d psi alpha, and here, sorry, psi alpha x psi alpha x is equal to minus psi alpha x d psi alpha x, and this is equal to 1. The rest falls. So if you have higher powers, and then if you do, if you apply these rules, you can easily recover well-known logarithmic singularity of the specific heat in the vicinity of the critical point. So first you have to compute the partition function z, and here, sorry, I didn't mention this too. It's a temperature parameter which is defined like this. But then you can simply redefine the coupling constant, so you can easily make Tc equals to 1, so just like this. And this parameter is considered to be very small. In this case, pardon?
So you write psi bar as sigma 3 psi, and then you define sigma 1, sigma 2? Or on the right of the psi.
Here? Well, these are Pauli matrices. So sigma, okay, I'll add here. So this is equal to 1. Sigma 1 matrix is 0, 1, 1, 0. Sigma 2 matrix is 0, 0, minus I. And sigma 3 is equal to I minus I 0, 0.
No, the question was why you have this symbol delta with head that you are not using anywhere.
This? This?
Over there. Yeah. It's a derivative.
It's a derivative, but derivative defined this way.
Thanks.
One confusing thing. I think this is really an action rather than the Hamiltonian.
Sorry?
It's an action functional rather.
Well, of course, I'm using it's a bad terminology, but it came from physics. Okay, it's an action, of course. So for the partition function as a function of tau, you have to integrate over all psi's minus h of psi. And then with using these rules, you easily find that it's equal to determinant, a square root of determinant of this object to power 1/2. And then for free energy, which is minus logarithm of z, you easily find that it can be represented as a minus L square, and then trace over this matrix of log, so it becomes d dp over 2 pi squared log of p squared plus tau squared. And then you easily find that it's equal to minus L square tau square ln 1 over tau, no, ln, sorry, tau plus constant. So we are talking about the singular part, okay? So if you like to know the specific heat, which is minus d2 d tau squared, F2, you differentiate and you get logarithmic singularity. You are getting that it's equal to, it's of the order of L square. It's a volume of our two-dimensional system, ln 1 over this. So that's a pure system, well known many years ago. Now I'm going to use this type of formalism for the case when the system contains quenched disorder. First, disorder is weak, so we are not talking about spin glasses. We are not. It's just we have a ferromagnetic system like this and modify slightly the effective tau which is over here. So the starting point for the random system is to say that instead of a tau which is constant, it contains plus delta tau which is space dependent and quenched. So this is a situation of thermodynamics of system which has a quenched disorder. So just general introduction to this, which I will use for the Ising model. Now, a general case. We have, for example, we have a
sorry, just a question.
Yeah.
Can you lift up the board so we can see what is behind? Thank you.
It's like this.
Thank you.
Okay.
When you say tau is much smaller than 1,
Yeah.
you mean you're at a very high temperature?
No. It means that tau is the temperature minus temperature critical. It means that we are very close to a critical point.
Yeah, that's right. Tau is T.
Tau is
like-
T minus Tc.
I saw Tc over Tc. I saw Tc.
No, here I assume that Tc is equal to 1.
Yeah.
And then it becomes T minus 1. So temperature is close to 1 and 1 is the critical temperature.
So you mean tau minus 1 is small.
No.
Yeah.
No, this is temperature. And this is tau. Tau is small. It means that T is very close to 1.
Tau is a measurement of how close you are.
Yeah, that's why it's written there. It's. I understand.
Okay.
It's okay. Can you lift?
Okay. So I'm going to consider a system with disorder. And here comes replica technique. Sorry, I know. Take it easy. If we have, instead of homogeneous system, some disorder, for example, we will have the partition function which depends not only on 2, but delta 2, which is a function of space. And this is random with a given distribution. So it's a random thing. We are getting a partition function which formally is also random objects. Then we can define the free energy. By definition, it will be also a function of tau and delta tau, which is minus log of z of tau and delta tau, which is also a random thing.
So there is no random magnetic field.
No.
Just, yeah.
Well, in principle, you can consider that, but it's almost hopeless. So then comes, this random thing is almost useless for study because it contains infinite number of parameters. And so here comes the concept of self-averaging. That people say, look, instead of this, we have to consider average value of f. Why average? Because then it's not a theorem, it's just argument that if we consider macroscopic system, it can be splitted in a macroscopic number of macroscopic regions, which are also, and then, so the free energy of a total system is the sum of infinite number of random things. And if the system is normal, if not pathological, then presumably, according to central limit theorem, the final thing will be given by just the average of that. That's the argument. It's not always working, but so usually people, if it's not about something very specific, people would like to know f average. Average over disorder. So it means that you have a problem of averaging logarithm of 2 delta 2, like this. when we consider critical properties at close to Tc, then it's much more delicate, because then the system is effectively described by the regions of the size of the correlation length, which at Tc diverges. And so this argument about self-averaging becomes even more sleepy. Okay, but okay, for the moment it's like this. If we do not touch non-self-averaging, you have to compute that. To compute that, one introduces average of moments of the partition function. So you take this, which by definition is equal to e to the power minus beta inverse temperature f, this f. And then if I take both sides of this equation to power n, I will get z to power n is equal to e to the power minus beta n f. And then if I average this over disorder, on the right I will have this p of f df. And this is a distribution function of random free energy. Okay, and then okay, this thing we can call z of n. So look at this part. If n is not integer but anything, you can always say that what you have here, it's a Laplace transform of the distribution function. And then, at least formally, if you are lucky to analytically continue this n, first you have to compute this for any n. And then in a lucky case, if this object is good in a sense of behavior with n, you can analytically continue this n to the whole complex plane. And then you can recover p of f by inverse Laplace transform. Yeah.
What is the relation between n, this n, and the size of the system?
No relation.
No relation.
I take
because if the system is very large, then the maximal value of it or minimal value of it would matter only. Naively.
And it will go to
will depend on okay. If the system is macroscopic, size goes to infinity. And if we are not talking about the critical point, then of course this converges to a delta function. And that's the case of self-averaging. And that's indeed so. But I mean, if I will be lucky to finish my talk today, I will arrive eventually to non-self-averaging situation. But this is a, okay. Then if you want to know only, if you do not look for the distribution function, but you are interested only in this, then it's much easier. Still, you have to analytically continue this function to arbitrary non-integer n. And if you take limit n to 0 on both sides of this equation, then you will get this limit n to 0 1 minus z of n divided by beta n is equal to this df p of f, which is f average. If you expand this in n, first term 1 and its normalized distribution function, which gives this one, and next term gives you the average value. So if you are looking for self-averaging free energy or in other objects, you need just to make this trick with n goes to 0. If you are looking for a distribution function, it's more tricky. Okay, so I come back to the Ising model with quenched disorder. In this case, instead of that pure system Hamiltonian action, we will have this dx psi psi plus 2 plus delta 2 is a function of x, psi, psi, like this. And now we are getting a quenched random thing here. Now, now I am going to start this procedure with replicas. I have to say that, in fact, when that was the story of 40 years ago. When we, with my brother, were doing this, of course, that was not, that we realized later. We were doing it honestly on a lattice, averaging over logarithm of the partition function. Were awful. But by the end of the day, you find that all this diagrammatic representation which we get for the renormalization group procedure nicely reproduced in terms of this formalism. Just one-to-one correspondence. So there is no need to come back to the lattice. This is
you don't actually need replicas, right? You can just do it. Everything is going to be perturbative
sure.
around the clear system. So you don't need replicas at all.
Yes, sure. Sure, but then you find that, in fact, after all that, you discover that you can reproduce exactly the same thing using this formalism.
There's an equivalence. You can do it directly.
Yeah, yeah. But sometimes it's more convenient to do it in a more compact way. For example, today I'm going to explain how it works using this replica formalism. So I'm going to compute z of n and 2, oops, which is the z of 2 delta 2 to power n average over delta 2. And it's assumed that delta 2 statistics is 0, that it's Gaussian distributed. X prime average is equal to minus 2 or plus u naught delta x minus x prime, and it's Gaussian. Then if you average this, it's what? It's you have a product over a from 1 to n d psi a. Now there are n fields. And here you have minus d2x sum over a to n psi a. I'll make it like this, psi a. This is a regular part. And then there is a random part, which is delta 2 sum over a psi a psi, like this, okay? And then if you average it with these rules, with Gaussian, from here you are getting it square. And in this way you arrive to the situation that that n can be represented, and 2 can be represented as a d psi a of all this. Exponent minus h, which depends now on n psi, replica Hamiltonian, so where hn of psi is d dx, and here you have a regular part, n psi a d plus tau psi a, and from here you are getting interaction AB, you know, AB psi A psi A psi B psi B. So due to randomness, you are getting before it was free fields. Okay, now they interact, and that creates a little problem. But this theory in 2 dimensions is exactly renormalizable, like the scalar field theory in 4 dimensions. So for this action, you can easily write renormalization group equation for this and for this. For the mass term, this is a mass term, and this is an interaction term. On diagrams, you can represent, so this thing, too, you can imagine as this diagram, and here you have to make number of replica, which is here, and this is a tau. And for this term, you have a diagram like this. This is a replica A, this is a replica B. And then from here, you compose all kinds of diagrams which renormalize this and this. It's not that difficult to do. Maybe I'll skip slightly some details. So the renormalization group equations, oops, wow. It will remain there forever. Oh, no? Ah, okay. So for this, for the interaction term, you have three types of diagrams like this. Plus this is A, this is B, plus this is A, and this is B, and then like this, A, B, C. For this object, you are getting only two diagrams, like this, and plus so with a little bit of patience, you easily get the renormalization group equations du as a function of scaling parameter psi, renormalization group parameter d psi is equal to minus 2 minus n over pi u squared, and for 2 you are getting d over d psi 2 as a function of psi is equal to minus 1 minus n divided by pi 2 n u. So in fact, you can put here, and then it will be d psi of the logarithm. And then now a little bit of magic of replicas, that the rule is that whenever you are getting n as an analytic parameter, not like there, so you sum from 1 to n. If it's analytic parameter like here, you can always put it to 0 right away if you are interested in this limit. So in the limit n to 0, it becomes du d psi minus 2 over pi, oops, u squared, and here d over d psi log tau is equal to minus 1 over pi u, which can be easily solved. And the solution is extremely simple. You are getting the solution like this. U of psi is equal to u1 plus 2u over 0 over pi to power minus 1, and tau of psi is equal to
where is the psi?
Sorry, psi is here. Sorry, psi minus 1, and this is oh, there is nothing like you know, okay. And here you have tau initial value 1 plus the same 2 u naught over pi psi to the power minus 1/2. This is a formal solution of equations. And you see that when you consider psi to infinity, so large scale, you find the zero charge asymptotics, because this goes like 1 over psi to 0, and this goes like 1 over square root of psi to 0. But it doesn't matter that you can drop the interaction term. Well, of course you can say that at infinity it disappears, but if you're interested to compute something like specific heat, you have to be more careful. Because for specific heat, what we have? Specific heat is given by second derivative of free energy over tau squared. If you differentiate that action over tau, you will get 2 times the thing like this. This is at the point x, and this is at the point x prime, and you have to integrate over x prime. And so, in fact, you can represent diagrammatic as this, like this. So this is object like that. And then in the zero charge regime, there is a special technique which was designed in the 60s, I think, or at least it's 70s, which is called parquet diagram. So you start again all this machinery of renormalization group, but it turns out that in this particular case, you can combine all the contributions here. So instead of point, you are getting thing like this. You all collected here and here. And this is a free fermion propagator. So effectively, for the specific heat, you arrive eventually to the situation like this, in momentum space. Squared tau of p over tau squared. And here the propagator, which for the free fields, it's 1 over p squared. Anyway, and this is a scale-dependent temperature, which is given by the renormalization group. You put this solution there, you easily integrate, and by the end of the day, I need some space.
There is another board behind.
Maybe I'll, because
There is another board behind.
here?
Yeah.
The third one, wow. Okay, great. So after all this integration, you find that C of tau is equal to 1 over 8 u naught log of 1 plus 2 u naught over pi log 1 over 2 absolute value. And then now you see that presence of disorder creates a new temperature scale from here, because either this is small or it's large. So you find that there is a tau with a mark u, which is of the order of minus pi over 2 u naught. And then if your tau is not too small, so that in the first case tau is still much bigger than 2u, it's small but not that small, then you can expand. Then this contribution is small compared to 1. You expand, you q u naught, and you are getting again ln 1 over 2. Pure system specific heat. Otherwise, if tau is much smaller than this, so you are much closer to Tc, then this dominates. You can drop 1, and you are getting, this is the case number 1, and here you're getting case number 2. It's 1 over u naught, ln 1 over 2, like this. This is case 2. So the singularity remains, but it becomes much weaker. There. Then, in preamble, it has to be said that initially there was this Harris criteria who said that if the specific heat characterized by the critical exponent, which is positive, so that the specific heat is divergent, then the presence of disorder is essential, otherwise not. Ising model is a marginal case because alpha specific heat there is 0, but ln log the tau divergent, so it was initially assumed that presumably divergency would produce the situation, would make the situation when the disorder is relevant, and indeed it's so. So that was the introduction. Now I come to the question of non-self-averaging. What happens? Oh, yeah.
How much is known about the higher loop correction to this?
I don't understand.
How much is known about the higher loop correction?
Look, of course, this is not exact. If you introduce higher loops, you correct it. In fact, you are getting contributions. It becomes a mess. But the contribution comes like this: ln, 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 or tau, and 3 and 4, and so on. So that's. Of course, you.
Marginally irrelevant.
Yeah. So in principle, you can add high orders, but then you are getting contribution of this type. Okay.
May I comment?
Yeah.
The replica action has OM symmetry. And myself, I proposed an exactness matrix years ago, and I imposed a form factor massless program, and I compute the correlation function. So this might also solve all the story of the loops, and because it's not a perturbative approach.
Oh. Okay. Well, okay. So this I can remove. That was just a. Now I want to investigate what happens when I want to get this distribution function. I will be talking about two objects, the internal energy and the specific heat. Because free energy, it's done, but it's not measurable object. You can measure internal energy, you can measure specific heat. And for the internal energy, on one hand, it's very easy because internal energy is given just by the derivative of df over the tau. So if you know, I've computed the free energy, take the derivative and it's done. But it doesn't tell anything about the distribution of this thing because it's just an average. I want to compute something of this kind, but not for free energy, but for internal energy. I have to construct a procedure which allows to introduce in such a way the distribution of this quantity. And for this quantity, oh, sorry, it's plus. For this quantity I want to represent like this. Limit epsilon to 0 of free energy as a function of 2 plus epsilon minus f of 2 divided by epsilon, okay? No doubts, it's a derivative. Then it means that if I keep epsilon finite for the moment, at the end I have to put it to 0. I can represent the same thing like this, epsilon equal to f2 plus epsilon minus f of 2. Okay, then if I put it to exponent, I will get this times e to the power minus. Okay, but this thing I put minus here, plus here. And then on the right-hand side, this can be represented as a partition function at temperature tau plus epsilon. And this is partition function to power minus 1 at tau. Okay. Now, I start replica machinery. I want to study average of the nth power of this thing. So I will have e to the power minus n epsilon e. And on the right, I have z to power n of tau plus epsilon, z to power minus n tau plus epsilon. Whoa. If I take average on both sides, tau. If I take average, here I would have this P of E, which I'm looking for. This is the goal of the calculation. On the right, I have average of this thing, which looks awfully because you have a denominator to power n. It's not at all the same as this, where you can average easily. This cannot be averaged easily. But then next step of this magic rules or machinery, this can be represented as limit m, another integer, m, which is first integer and then 0. Z tau plus epsilon to power n, z to power m minus n to average. Initially, and this can be called as z of m, n, and all this tau plus epsilon and all that. So the procedure is this. You have to compute this thing for the case m integer bigger than n. So both things are positive. So altogether here, you have m replicas, because here n plus m minus n. And this is durable. This can be done. Then if you are lucky and the result is analytic in both letters m, n, you take this limit. And then you are getting this thing more or less like there, because on the left you have a Laplace transform of the distribution function. And then maybe it can be recovered via inverse Laplace transform. So the main thing is to compute this. And then let's see what happens. Okay, I need that stuff. Which way I can?
There's a stick.
Wow. This one? No. Ah, I see. No. So in this case, we'll come more or less to the same formalism, with the only difference that now in the effective action, here the mass term, which depends on the replica index, and there will be two types of tau. The rest is the same. There will be tau A is equal tau plus epsilon or tau, depending on the number of replicas. For A equal 1 n, and here for A equal to n plus 1 m. The rest is the same. Then you come to this. Here it will depend on A. You will have the same stuff here. You can write down renormalization group equations for two types of tau, this and this. Except there will be three equations for the charge and for two types of mass term. They can be solved.
There is some minus somewhere, no?
minus where?
Well, coming from the formulas that are behind on this.
Here?
Yeah, because you are subtracting these two down.
No. This is, you see, when I
Dividing Zn over Zn minus n.
no, here now we will have this. Wait a minute. I'll wait. It will be like this. Z of mn to epsilon will be given by product from 1 to m. Then here from 1 to m, and here, it's here, sorry. Z m n to epsilon is given by the replica Hamiltonian, in which you have sum to m, which depends on index. Here AB to m. And so the same diagram, the only difference is that you have two types of two. So you have three equations. They can be solved. And to finish my story, I have to skip slightly technique. But I want to say that by the end of the day, you are arriving to this you are getting the relation of the you arrive into this. You have to take limit m to 0, limit epsilon to 0 of this thing, z of m, n, 2, and epsilon. Okay? And if this limit exists, then on the left-hand side you will have this. But the parameter of Laplace transform is not n, is not epsilon, it's a product. And so if you are getting something mixed, no hope. It means that the machinery doesn't work. But in this particular case, it turns out, so I will put this as a z over epsilon n and 2, like this. So this can be called the parameter of Laplace transform.
When you put it already to 0.
I put epsilon to 0 and n to infinity so that this is finite.
But n should be smaller than m.
M is already 0.
No, but what you did before.
Yeah, sure.
N was always greater or equal to 0.
0, here n, and here m.
Yes.
Now we computed for this case. Yes. Then we are getting analytic function of these two letters. And then I put this m here. Okay. And keep n here. That's it's a magic procedure. So
can all this be calculated via supersymmetric method?
Oh, no idea. No idea. Maybe.
Because all these problems will.
You see, usually, if you are getting something reasonable in replicas, it's almost always correct.
Except when it's small.
So the relation you are getting eventually is like this. This z of s and 2, this object, in the limit when the limit is taken, is equal to e to the power minus e of 2 s minus e star of tau s squared. S is this. And what is funny is that you are getting nothing else. I mean, in all these manipulations, you are risking to get a lot of various combinations, epsilon n, all that. There are only two terms, epsilon n linear and epsilon n squared, and nothing else. And then it's done, because this thing is equal to this, where here you have s. Oops. Here you have S, and then it's a trivial thing to recover P of I. It's Gaussian, but the point is, what is this? These two things. I of 2 is equal to proportional to, if you want. I will skip L square to ln 1 plus 2 over pi u naught ln 1 over 2. And this is this. If you have a linear thing, it gives you average free energy. And fluctuations of the order of L log 1 plus, again, 2 over pi u naught and 1 over 2. So you are getting the Gaussian distribution, which looks like this. So for the distribution function of internal energy, you're getting, well, proportional to e to the power minus e minus, let me put it here, 0, average value squared divided by 2 e étoile squared. This is the average. These are fluctuations. Done. Now we have to analyze what happens in the critical point. Because if I put L to infinity, keeping to finite, you are getting a delta function. It's okay. I wonder what happens if I put tau to 0 first. But I cannot do it for finite L. It can be big, whatever you want, but if L is there, you cannot put tau 0, because the correlation length which comes to the system size, and then you have to stop. So if you want how it's called, pseudocritical point is tau of the order of 1 over L. And so if you put tau like this, and you look what happens as a function of L, you find that this becomes average. You see, it's L. And if it's the dominate, it's ln 1 over 2. And this becomes exactly the same. The only difference is that here you have 1 over u naught, and here you have divided by square root u naught. So it's 1 over u, and this is a 1 over u naught L, ln 1 over 2. So you find that in this case, the fluctuations, sample to sample fluctuations, as a function of L, is of the same order of as the average energy. And it's just a case which can be called non-self-averaging, because your distribution function keeps finite. It does not transform. It's not a delta function anymore. Okay. That's one thing. And you see, it's not extensive in L. It's a square root of the system, of square of it. And then to finish one more chapter, I skip to the result. I want to say that it's not that evident that you are getting always things like that when you sit at the critical point. Because if you repeat the same machinery for specific heat, which is a second derivative of free energy, the same type of manipulation that you second derivative of F you change by 1 over epsilon square F tau plus epsilon plus F tau minus epsilon E minus F of 2. Then you will repeat all this stuff, but mass term will be represented in 3 ways. Here there was only 2 of them, now there will be 3 of them. But still it's durable, but by the end of the day you arrive to the distribution function of specific heat, which is just a delta function. There is no square term like this, only linear one. So the resume, if you want, is that a priori you cannot say from the very beginning what is self-averaging, what is not. The other thing is that although the dream was, I proposed something which is measurable, in fact, I'm not sure, because this is only the singular part of specific heat, singular part of internal energy. The main part is regular, and it's also random. So how to distinguish or separate one from another, it's a special procedure. I don't know how it can be done, but in principle, maybe. You see, when you have a divergence of specific heat, you can always say, okay, there is a background which is regular, forget, because we have a divergent peak. The other thing, when I say, look, there is a smooth distribution function of the thing which is still finite, compared to the regular part. Okay. So that's more or less all what I wanted to say.
We have time for a quick question. Yeah. I'm just wondering how much of this just follows from the general structure of the realization group flows, so that the disorder here is marginally irrelevant.
Yeah.
And the generic behavior for marginally irrelevant disorder is, I think you get a power of log t different than 1, log tau, and then there's a special case where 2 coefficients are the same, where you get the log 1 over tau. And I would have thought all of these quantities about the fluctuation quantities and so on sort of come from that general structure. You don't need the fermions anything. Once you know that's the behavior, you can get a lot of this.
Yeah, I think so. I think so.
Yeah.
It's like in 4 dimensions for scalar field. In D equals 4. You have a power of log here, it's just.
If not, let's make a very short break.